All right, so welcome to our third installment of working with an oscilloscope. In this episode, what we're going to do is we're going to look at using some of those complicated buttons that we've been avoiding since the beginning. As you can see, I already have some of the stuff set up, so let's just go ahead and get into it. All right, so let's pump the brakes a little bit here. Before we get into the actual setup, let's reacquaint ourselves with the oscilloscope that I'm using. So I'm using the Tektronix TDS 1002B. It is a 2-channel scope with a maximum bandwidth of 60 megahertz. And the buttons that I was referring to that we're actually going to start using in this episode are actually these soft buttons over here to the right side of the screen. We're going to start first by looking at the buttons or the functions related to channel 1. On my scope, in order to get the channel 1 menu over here on the right side of the screen, I just need to hold this button here until this information pops up on the right side of the screen, indicating that the soft buttons can control functions related to channel number 1. Now the first one we're going to start with is actually coupling, and so that's what we're going to look at on this oscilloscope. Now if you have an oscilloscope, you may want to find where the coupling information is on your oscilloscope. Just to help you out a little bit, I have a second oscilloscope here. This is an old analog oscilloscope made way back when, who knows how far back when. And you'll notice that the coupling related buttons are over on the right side. For channel 1, the coupling related buttons are over here. And for channel 2, the coupling related buttons are over here. During the break, go ahead and identify where your coupling related buttons are. Alright, so welcome back. I hope you had an opportunity to find where your coupling related buttons are on your oscilloscope if you're using a different oscilloscope. From here, what we're going to do is again move on to our coupling. The first one we're going to look at is coupling ground in particular. And before we do that, actually, let's talk about what coupling is. So coupling is just, in the case of electronics, we're actually joining two different signals, if you will, or two different lines or two different devices in order to merge them or combine them together. In the case of coupling as it's related to ground, if we look at this circuit here, so over on my left side I have an oscilloscope, and these lines here represent my probes or probe coming from the oscilloscope. As you recall, my probe had both a point where I can test and a ground connection. And then over here, this is a device that's actually generating some signal, and as you can see for this device, it has both an AC and a DC voltage source on the inside. What you'll notice is that there's a dead short over here in the oscilloscope. So if we were to couple and set the oscilloscope to ground, what happens is we're actually creating a dead short within the oscilloscope, which then gives us where our ground line is on the actual oscilloscope display. So now that you understand that, let's go ahead and see the physical demonstration of grounding for coupling as it relates to the oscilloscope. Okay, so in previous weeks, what we did, if we wanted to see the ground line on the oscilloscope, what we did was just simply disconnect our scope probe from the channel input in order to do so. Now we didn't have to do that, but again, since we're trying to avoid using the buttons, we did that. Now that we're trying to use the buttons, I'm going to show you how you can actually see where your ground line is without having to disconnect the scope probe. So currently what I have is scope probe connected to channel number 1, and then the scope probe is connected to the function generator right here, and going into its channel number 1. Okay, now let's zoom in a little bit on our function generator to see what signal is actually being generated. So hopefully the camera focuses. If not, we're gonna have to do a little bit of trickery here. All right, there we go. So as you can see, currently the function generator is producing a signal that has a frequency of 1 kilohertz, an amplitude of 2 volts peak to peak, and a 0 volt offset. Okay, so now if I wanted to, let's say, go ahead and I'm gonna readjust the screen here just a little bit, go ahead and see where the ground line is, and in other words zero out the signal that's actually being produced, and that signal is currently that 2 volt peak to peak with a frequency of 1 kilohertz. Okay, if I want to ground that out, what I'm going to do here is go over to the area where it says coupling, and you're going to notice it says coupling DC. If I hit this, push this until it gets the coupling ground, you'll then notice that my signal goes away and I can see my ground line. Now, just in case it's a little bit tough to see, what I'm going to do is I'm going to actually show you what it looks like by capturing the screen. Alright, so I went ahead and captured what was on the screen a minute ago. And so if you look on here, you'll notice that the coupling for channel 1 now says that it's ground. And also you'll notice that the signal is just a straight line that goes across the screen. So again, this is how you would do coupling on this oscilloscope, and this is what you should expect on your oscilloscope when you figure out where your grounding or where your coupling buttons are. All you have to do is hit the ground or position it to ground, and you should see approximately the same thing on your screen. Alright, so for the next two examples that we're going to look at here for coupling, we're going to set one configuration on our function generator just so we can see what's the difference between AC and DC coupling, which are the next two. So let me go ahead and focus in on the function generator, and I'll set that so you can see what that one setting will be. Now let's back out just a little bit there. I'm going to adjust the lighting in a little bit. Alright, so as you can see, the current setting is 1 kilohertz, 2 volts peak to peak with a 0 volt DC offset. I'm going to go ahead and change it so that it has a 1 volt DC offset. And so that's 1 volt. Change VDC, and so now you'll see it has a 1 volt DC offset along with the 2 volts peak to peak. Okay, and again, I'll use this one configuration, and since you've already seen where I changed my coupling on the oscilloscope, I'm going to go ahead and just capture what's shown and put that onto the computer screen. Alright, so now let's look at DC coupling. And so before we get to the actual results from our DC coupled signal coming into the oscilloscope, let's talk about what DC coupling is. So again, we're looking at a diagram here, a very simplified diagram I should add, of an oscilloscope with some internal resistance. We have our probe here, which has a very, very, very small amount of resistance. And over here in this case, we're using this to represent our function generator, or the function generator that I showed in the setup. Now, this function generator is both providing a AC voltage, and it's providing a DC voltage. When I'm ready to test the function generator, I'm going to go ahead and connect this probe into the positive terminal out of the function generator, and I'll connect my ground here to ground here so that I have a common point ground. Now, what you'll notice from the previous diagram where we had our coupling was set to ground, there is no longer a short across here. So because there's no longer a short, what I should see is whatever signal is coming in here. Now in this case, again, I have both an AC voltage and a DC voltage. So because of that, I should expect to see both on my oscilloscope. So let's see now what I see on my oscilloscope. So if you look here, this is a screen capture of what I captured from the oscilloscope. Remember, we're doing DC coupling, okay? And remember my oscilloscope, or pardon me, my function generator was set to 2 volts peak to peak with a 1 volt DC offset. And so if you look here at this signal, the 1 volt DC offset is actually cause a signal to move from being about this line down here, which would be our ground point. It moved it up by 1 volt. And that's the effect of adding the DC voltage to the AC voltage. It moves a signal, that AC voltage, which we said was 2 volts peak to peak. So we have 1 volt here, 1 volt here, so that's a total of 2 volts peak to peak. And so it moved that signal, that 2 volt peak to peak signal, up by 1 volt. And again, for this signal here, we're doing DC coupling. Our voltage per division is 1 volt per division, and so therefore from peak to peak, what we can see here is we have 2 volts peak to peak, and it's been moved up by 1 volt from where our ground line would be. And so again, that's the effects of doing a DC coupling. Both AC and DC are allowed to come into the oscilloscope. Now our equation for the signal that's here, if we were to look at it mathematically, it'd be V of t, which represent our voltage along the y-axis here with respect to time. Remember, time is on our x-axis, and so the one that's here in this equation, this one that I'm pointing at, represents the DC offset, and then I have plus 1 sine of 2000 t times pi. Now the one that's here represents 1 volt for the maximum amplitude in the positive direction and 1 volt in the negative direction, which gives us a total of 2 volts peak to peak. And then remember, for our frequency, I set the function generator to 1 kilohertz, and when I multiply that 1 kilohertz times 2, I end up with that 2000 that's here times t times the pi. Okay, so this equation here is a mathematical representation of what I'm actually seeing on the screen. So let's go ahead and switch this from DC to AC coupling. The reason why I'm actually showing this is because something interesting happened that I believe that you may need just a little bit of guidance on. So again, I'm going to change from DC to AC coupling. And if you notice here on the screen, it seems like the signal looks a little unstable. The oscilloscope cannot lock in on exactly where the signal is. If you do the following, you can do one of two things. You can go to the trigger level over here and bring that trigger level down, and you'll notice the trigger level is indicated by that marker there. Actually, when you bring it into range of the signal, it actually stops it from moving. That's one way to stop it. Now, that's something I'm going to talk about next week, but I just figured it's something that you may need to know. Make sure you don't panic when you see it happening. Another way to prevent that from happening, and I'm going to go ahead and make the signal unstable again. Another thing that you can do in order to stop that from happening, you can actually hit auto set. If your oscilloscope has an auto set button, you can hit auto set, and what the auto set does is it lets the oscilloscope go ahead and try to figure out what's the best settings for your screen to be set on. Now, I personally don't like using it because it's more of a, giving control over to the actual oscilloscope. If you're going to be an engineer, or you are an engineer, or you're an electronic technician, it's always good for you to have control over your own scope. So again, those are two ways to actually stop or allow the oscilloscope to stop rolling. All right, so let's now talk about the AC coupling and what it means when our oscilloscope is set to AC coupling. So for AC coupling, what happens is this: any DC signal that comes in on the test probe is pretty much discarded by the oscilloscope, and the oscilloscope only looks at the AC signal that comes in. In order to do that, it needs to actually add a capacitor in series with the signal that's coming in. So I have, again, this very simplistic model of what's going on. And so I have my oscilloscope here with, again, a very high amount of resistance inside the oscilloscope, and we now have that capacitor. And please ignore the N that's there. We now have this capacitor that's in series with the signal that's coming in on the test probe. Again, we have a very low amount of resistance, low relative to what's in here. And we have our ground. This is going to represent the function generator. And again, for our function generator, remember we have it set to 2 volts peak to peak, or 1 volt peak, which is the same thing. And we have, in this case, a DC offset, and the DC offset is set to 1. And so we put our test probe here to this, to our function generator, connect our grounds to grounds. And so that's pretty much what's going to be happening here in our circuit. And you saw what the connection looked like before. So now let's look at what the result would look like once we've, of course, stopped the oscilloscope from having the signal roll on the screen. And so this is what the signal looks like. Again, we're doing, we have AC coupling. And what you'll notice here is that even though we had some DC, it's now been pretty much discarded. And so now our AC signal here is about our ground line, okay? And so now we have 1 volt above the ground line, we have 1 volt below the ground line. Remember, our volts per division here is 1 volt per division. And so pretty much you can see that the DC has been discarded or the DC signal has not been allowed to be read by the oscilloscope. And that's all because of putting that capacitor in series with the signal that's coming in. Now, the signal that's actually shown on the screen here mathematically looks as follows: V of t, which is equal to 0. So what's on the screen does not have a DC component, so that's why this is 0, plus 1. And that's your voltage peak here. So that's from this point to this point, or you can look at it from this point to this point, whichever one. The thing is the magnitude of those 1 volt peak, sine of 2000 t times pi, or you can say 2000 pi times t, whichever way. It's still the same. And so again, this is the mathematical representation of what is on this screen, and what is on this screen is AC coupled. The DC has been thrown away. All right, so here's a good question. What happens if we have our oscilloscope set to AC coupling, but there's no AC signal coming in, it's just a DC signal? So to show what happens, if you look, I have my oscilloscope, I'm looking at channel 1 still, and this time, rather than having the function generator on, I now have the power supply on. The power supply, the DC power supply, and so it's connected to my oscilloscope, and that is connected here, okay? And so that DC signal is now going into channel 1, okay? And what I'm going to do now is I'm going to focus in on my oscilloscope. Let's try that again. All right, let's do it this way. And I'm going to adjust the lighting here so you can see the oscilloscope. And you'll see here, it may be a little tough to see. Again, I'll show this as a screen capture after. So you'll see here that my coupling says that it's on AC. Now remember, it's connected to the 5-volt voltage source over on my left there. And what you'll notice is that I'm just getting a ground line here. Now if I was to change that AC to DC, you'll see that now that line jumped up to the top to represent I'm now getting 5 volts into my oscilloscope. Okay, and so again, I'll show this on as a screen capture, but I wanted you to see me actually doing it on the oscilloscope. Alright, so the last major button that we're going to look at in this video is related to the probe X voltage, and I'll tell you what that is related to. Let's say you come about a scope probe that doesn't have one of those switches on it, like the previous oscope probes that I've used. So this is one, for example, and you'll notice that there's no switch on here. However, though, what happens is it's already set to be a 10X probe. So this is what it is. You can't change it to a 1X probe or whatever. So if this is a case where you have one of these probes and you have to use it, and you don't want to go through the trouble of having to calculate or adjust for this if you're stuck at 1X with your oscilloscope, what you can do is you can use the probe 1X or probe voltage button if you happen to have one. Some scopes do have it. And so what you do is you'll hit that button and it will take you to a sub-menu that allows you then to go through and change from 1X to, let's say, 10X, 50X, 100X, or whatever, based on whatever probe you're using. So the best thing for you to do if you have just a 10X probe and it has no switch on it, just go ahead and match the amount of attenuation in this case so that it matches up, and then that way you don't have to do the calculations for the probe, or actually for the signal on the screen. Alright, so these are the last two functions we're going to look at, and I left these two for last because honestly I have not seen these on some of the most common or some of the more used, I guess you can say, oscilloscopes. Actually, this is the first time I'm seeing them, and so for that reason I'm not going to spend a whole lot of time on them. First one I'm going to look at or point out to you is this bandwidth limiting button here, and what this just simply does is it allows me to switch from, let's say, 60 megahertz, which means the channel 1 in this case will allow frequencies from 0 to 60 megahertz. If I hit the button, it goes to 20 megahertz instead, so it only goes from 0 to 20 megahertz. So anything from 21-ish, let's say, up to 60 won't be allowed to come in, or will be attenuated heavily on channel 1. The second function here, not quite sure why you would need it, but it's on the scope, so I figured I'd go over it. The invert, what it simply does is this: it takes the signal, whatever it is, and it just flips it totally upside down and puts it on the opposite hemisphere, if you will, of the screen. So if you have something in the north part here or the top part here, it just takes that signal and flips it totally upside down and puts it at the bottom of the screen. All right, so that covers all of the soft buttons that we have there on the side as it relates to the different channel inputs. I just looked at channel 1, but of course the same thing is done on channel 2. I'm going to tell you guys, well done. This is the third video. And so now you're actually getting to the point where you're not quite a beginner anymore. I probably have about 1 or 2 more coming up. I definitely know 1 more, because I definitely need to talk about that triggering level that we kind of touched on today. So come back next week. I'll have the next video up related to definitely trigger is going to be on there, and a few other buttons that I think are going to be pretty beneficial to you. So have fun until next week. Keep exploring with your oscilloscope.